Let's come to the let's come to the second part of our lecture, lecture 2. What strategy I'm now opting is that I am uh, recording the lectures in audio, number one, and number two, of smaller duration, so that you can have you don't face any problem in downloading all this stuff. So I'll try to shorten, or I'll try to do some video editing with my first lecture, that is 102 MB. So I might get some parts in that as well, so I can upload that as well if I got succeeded in that format, doing some editing in that particular lecture. So this is the second part of this lecture. So let's go to the screen share and again go to the slide share. So here is the example. This is the example we are going to do for this gear problem, right? So now what we are having over here, we have a gear. We have a shaft over here. This is the shaft AB that is attached with this bigger gear, right? And diameter of this is 2.25 inches and the length is 1.5 feet, and attached with gear B. This gear B is attached with gear C, and this gear C is then attached with this shaft CD, and a torque of 8 kips per inch is being applied at point D. Diameters are given, lengths are given. Diameter of shaft AB is 2.25 and length is 1.5 feet, whereas the shaft CD is 1.7 inch diameter and 2 feet is the length of that one, right? RC of the gear C is 1.6 and R of the larger gear, RB you can say, is 4 inches. Material is same for all across the board, and the G of that particular material is 10,000 kips per inch KSI, right? So what we have to calculate? We have to calculate torsion at rod AB, torsion at rod CD, and angular twist of this point D with respect to this point A, right? So standard format is, we will first calculate, since these are all solid rods, so we will calculate J for them. JAB for this rod will be pi by 2, 1.25 raised power 4 is this much. And for JCD is pi by 2, 0.8754 raised power 4 is 0.92 inch raised power 4. Right, so this is straightforward because these are the straight rods, solid rods, so we have an idea how to calculate this moment of inertia for polar moment of inertia for rod AB and CD, right? Now question comes, if T 8 kips per inch is being applied at point D, so how much T will be at section this one? This is a section AA dash. So obviously it will be 8 kips per inch. TA at this, if I take the cross section at this AA, so it will be 8 kips per inch, right? And we know that this 8 the kips per inch will straightforwardly going to this gear, smaller gear at C, right? So if we want to calculate the shear stress that is being applied, being induced by this torque 8 kips per second applied in this counterclockwise direction, so that will be 8 into 0.875 multiplied divided by 0.92. So it is TC over J, right? This is the torque. This is the, sorry, this is TC over J, right? So this is T, this is C, and this is J, right? So this is T, C, and J, and we end up with somewhere around 7.61. So now TC, now the torque that is being applied at TC is 8 kips per inch. This is the torque. Not I am talking about the not torsion, torque that is coming at C. Now my question is, will that be the same torque at point B? No, it will not be the same torque. Reason behind, there is a size difference between this gear C and this gear B, right? C is a smaller gear, B is the larger gear. So as we have already discussed in first part of this lecture, that was if it is being transmitted from a smaller gear to the larger gear, torque will obviously increase. So TB, so torque at this point B will be 8. That is the torque being applied at this point 8 C, and ratio of the bigger gear versus the smaller gear, right? So it will be 4 into 1.6. So it will be 20 kips per inch into a kips inch, right? So this will be the amount of torque that is being coming on to this point B, right? Now my question is, what will be the torque at this section B? If I take any section over here, what will be the torque then? It will be the same torque that is coming at the point B, and that is basically the TB, right? So T at section BB dash, at this section BB dash, it will be 20 kips per inch. Now torque is there, so we can calculate easily the torsion at this particular point. Now torsion is 20 into 1.25, again TC by J. It will end up with the 8.8 and 8.95 KSI will be the torsion in the rod AB, right? So till now, this is a very simple problem. There seems no issue in it. It is pretty much straightforward, right? Now we come to the angular rotation. Here the tricks comes, right? So now the first thing you need to be careful is whenever you are want to calculate for that angular twist, so always you need, for in the case of the gear, always start from this fixed position, right? In this particular case, we have fixed position over here, that is A, right? If I shift it from here to here at this point D, then you must start from D and then come back to the point A. What we want to calculate? We want to calculate, in this particular example, we want to calculate uh, angular rotation of point D with respect to this fixed point, right? So we will start from A to B. A, right? And A is basically 5 BA. 5 BA means rotation of this point B with respect to A. That is TL by GJ, right? Torque, we know what is coming over here. Torque in B is basically, in rod B is, at any point in the B is 20 kips per inch, right? At this rod, it is 20 kips, right? Length is known to us. Length is basically 1.5 feet. We will convert it into inches. This is the torque, this is the G, and this is the J for this one particular one, right? So it will be 0.143 radians. That will be the deformation, that will be the angular rotation of this one, right? So now again, if this particular point B is rotating this much radians, is rotating 0.143 radian. What do you think that how much this gear will be having the angular rotation? Will it be same or it will be different? Obviously it will be different, because again size is there. And again, refer to the previous lecture, we have already seen that when we move from the larger gear to the smaller gear, generally deformation increases, and vice versa. If from the smaller gear to the larger gear, angular rotation decreases. So we will take, what we will do, we will take the ratio of the larger gear versus the smaller gear and multiply it with the phi BA, and we end up with the 0.0358 radians. So this will be the one that will be the coming from the point D, right? Point C. Now again, this is the amount of the 0.0358 radians is the amount that this particular gear C is having, right? So what this shaft will be doing, will it be having same amount of angular deformation, angular twist, or it will be having different angular twist? It will be having different angular twist. Reason behind is torque is also being applied on this shaft, right? If it is torqueless shaft, then fine. How much this gear is twisting, this much shaft will be twisting. Your angular deformation it will be getting. But addition to that, now we have a torque of 8 kips per inch over here as well. So obviously the deformation, the angular twist of this shaft CD will be larger than the twist this particular gear is achieving, this particular gear C is achieving. So what we will do? We have already experienced in the last lecture as well. We sum up all the deformations. Right? So we reach at C gradually from rod AB to point B, and then point B to point C. So all are being added, all are being modified, right? But at this particular point C now, if we want to calculate phi CD, so then definitely it will be different from the phi C only. So phi DC will be 0.0358 plus 8 into 2 into 12 over this whole amount. That is the phi TL by, that is TL by GJ. That is because this is because of this torque 8 additionally being applied on that particular shaft. So phi DC will be 0.0566 radians will come. So now this will be the one, ultimately that particular point D, this particular point D will be moving with respect to the this point A. So this is how you need to calculate. You have to be very careful. Always start from this fixed point and then keep on going up to that particular point on which you want to calculate, and you have to see what should be added and what shouldn't be the added, because net net angular deformation, angular twist will be the sum of all angular twist. But in particular cases of the gears, it is a little bit tricky to solve this problem. But definitely you need practice, and then you will go ahead accordingly. Now I am going to share some of the slides from the which I forgot to do last time. Uh, for your reference, just because last time we could not I could not show these slides while recording my video. So these were the problems. 3.01 was the problem. I solved it. And then this was another problem that was 3. Sorry. So this was another problem, 3.1 I discussed, right? So you have to be just careful in these calculations, like the one over here. Like this is the one. Again, this is the ratios. You have to be careful where the torsion is minimum, where the torque is minimum, and you have to accordingly take these ratios. And then again over here, there was some point to be clarified. That was the same weight. So we calculate the area, and then accordingly we plan it from there. And then we have another, we have the same problem 3.2 over here. Then we discussed this one, and then we discuss this as in the detail as well in the last lectures, and then how to solve it. The TB, this TB will come in terms of TA, and then we will solve it, and this TB and TA will go into this equation to calculate both, because this is a statically indeterminate case. So this is for the transmission shafts. Principal transmission shaft perform specifications are power and speed. We have discussed in detail all about this. So these are the expressions we have already discussed. Tau max will be remain same, TC over J, right? And J over C ratio is, if we this one, J over C for a solid rod, we know J is pi by 2, C 4 divided by C. So C4, one of the C4 will be gone, so pi by 2 by C cube, and that will be T over tau max ratio. Likewise, if we have the hollow shaft, then J by C2 will be equal to this much expression, and you can prove it. Actually, these are two important expressions. Reason behind, whenever we want to calculate the diameter of the shaft, desired diameter of the shaft, so we need to calculate this C. So in the next few examples, you will see that how we will utilize this one. So these are very simple examples. Power of the motor is given, that is 5 horsepower rating. Running RPM is 3600 RPMs, and shearing stress is given 85,000 psi in this particular shaft. So P will be obviously 5 horsepower into 6600. If you remember, in my last lecture, I used the 550. That was in pound fit, but it is 6600 is in the pound inch. That is a conversion, simple, right? So P or the torque will be power or the torque. Here P is equivalent to the T I calculated last time, right? So it will be 30,000 pound inch, and F will be 60 hertz or 60 cycles per second, right? So sorry, this will be the T, not the power, torque. This will be the power, right? So torque will be P, sorry, torque will be P over 2 pi F, right? P is over here. So this is the same expression we are having over there in the torque. So in the torque, we need to divide this by 2 pi F, right? So what we did in the handwritten notes, right? So P over 2 pi F, and we will end up with the 87.54 pound inch. Now J by C is T over tau max. Tau max is given, that is 8500. That is the tau max, and T is over here. So JC will be this much amount. And now we know JC for the solid rod is pi by ratio of J over C is half pi C cube, and from here J we can calculate J over C is half pi C cube, and half pi C cube is equals to 10.3. This is the one over here, right? So from here we calculate the C, and from C, if we multiply it by C, is basically, we know C is the distance from the center to the maximum outer periphery of that particular shaft, right? So if we want to calculate the dia, so it will be twice the amount of c, so it will be 2c, obviously that will be the radius. So 0.374 inches will be the shaft diameter that should be used if we want to if we want that stress should not exceed 8500 psi when it is driven by a 5 horsepower motor, right? Similar case with the over here as well. Again, we are calculating the difference. Now it is basically for the tube, right? Yes, it is for the hollow shaft, because outer diameter is given, we have to calculate the inner diameter of the shaft. So same pattern is being followed, right? Here we are using J by C2 ratio is pi by 2 C2 into C2 outer radius, outer radius minus inner radius, and from there C1 is calculated, that is 4.4 a millimeter. So tube thickness should be 5 millimeter, around 5 millimeter should be used for this much area, right? Again, this is the one we have already discussed, so you can calculate, you can look into that as well, there seems no problem. Again, you can see phi b is equal to rc over rb. So phi b is this one, we are going from larger gear to smaller gear, obviously the deformation or the angle of twist will be more for the smaller gear. So you can see that the phi b for the gear b is 2.8 times larger than the phi c, right? And then you can calculate torque max for both shafts, and then you can calculate phi b for all these shafts accordingly. So that's all enough. This is the chapter 3. I'll send you the examples and the problems that need to be solved, and that need to be looked into that for you guys from the exam point of view. I'll give the details of the all sections which we covered in this chapter, as well as all the or the relevant information about the numericals and the problems and the solved examples. So we will I'll update you accordingly so that you can you can prepare them for the from the exam point of view. So thank you very much. Best of luck. एंड अल्लाह ताला खैर वाफिक रखे जनाब, बहुत शुक्रिया, थैंक यू वेरी मच।